skills like this very regularly. I think that this is kind of one of those exercises that if I'm ever out with a sick kid, or if I'm out sick or something, this is something that I usually leave copies of for you guys to work on. It's a good little logic puzzle to make yourselves go through. All right? Terrible?
No.
Did you get most of those, though? I mean, if you got through the last names before you have to try to really figure out backtracking, because that's when things can get really messy, and it's not the end of the world. Like I said, this is just an exercise to make sure that we understand how things are related, and you're using reasoning skills to make sure things work themselves through. So let's take our notes here from yesterday. There's a few things that I want to reiterate of some of the definitions we kind of glanced over rather quickly yesterday. And we're going to work through a couple more examples, talk about other ways that things work, and show how they're related to the vocab, and how does this all tie to actual math that we haven't really done yet besides the number 29, that kind of stuff. We're going to look at how does this relate when you throw in vocab into a problem. So, let's see. One of the main definitions of things that we talked about yesterday, and this is still section 2.1. We're just going to get into a little bit last bit of the definitions and a couple of the vocab things we kind of glanced over quickly yesterday. One of the main things that we talked about yesterday was this thing called conjecture. And what this conjecture, you actually did this throughout the exercise of those logic problems. What you were doing is you were making an educated guess given the information that you had in front of you. So what we defined yesterday as conjecture was basically an educated guess. Oops. And I think we talked about what makes a guess educated versus just a random guess yesterday, didn't we? How would you define the difference between the two? Yeah. Okay, yeah, number patterns. So you're figuring out the differences between the values to come up with the next number, and just instead of saying 6. It's fine, because 6 is a guess. You guys do this on multiple choice tests. Did you know that? When you have multiple choice tests, you've got A, B, C, and D. Sometimes there's an E in there, but more often than not, there's usually 4. Now, when you do that, there's obviously one right answer. When there's one right answer, that means there's how many wrong answers? 3 of them. So what they normally do with the 3 wrong answers is that one of them is really close to the right answer. It's that one silly thing you could have done wrong. Switch the sign. And that's very common. The other 2 answers, usually one of them is what you call a distractor. It makes no sense at all, but it makes you look at it going, man, I really, really screwed something up, or I might not have really screwed something up. It's one of those things. And then obviously then the last one is also something like one simple mistake thrown into the problem. So a lot of times when you're looking at multiple choice stuff, you can kind of figure your way and use logic to see, okay, how did that actually work? And as we get into some of those test taking skills or skills of test taking like that, I'll show you guys how you use logic to come up with the right answer, even if you don't know how to math. Okay? A lot of times it's in front of you, you just have to read through it to show what doesn't work. Does that kind of make sense? So if you've ever taken an educated guess instead of just randomly picking D on a multiple choice test, you've done this. Okay? The other one that we did with conjecture was this thing called a counter example. And yesterday we defined the counter example as what? Do you remember? Yeah. Anything that disproves something, your conjecture, or whatever you want to call it. excuse me, you probably came across this if you were working on those logic puzzles. If you were working on those logic puzzles and all of a sudden you thought somebody was in this one camping spot and that was your educated guess, and you're like, oh no, so-and-so is there because they couldn't be there because somebody else was. You come across, you're taking a guess at something because you think it's going to work, but yet you figure out otherwise that it's not. I think the example we gave in class was the statement, if you are a teenager, then you are 15. That's not necessarily true because you could be 16, 17, 18, 14, 13. You can be any of those teens. Okay? That would be a counterexample. We'll talk about more of this idea of a counterexample and how that's going to look when we talk about it in terms of math here in a little bit. I'm just kind of revisiting our definitions so far. And the reason we did both of those two was kind of the main thing of yesterday, was doing this idea of inductive reasoning. Inductive reasoning. And the way that we were defining inductive reasoning yesterday was using patterns, using information to come up with a conjecture. You're using given information to come to a conclusion. Oops. And I kind of worded that a little bit different. This idea of what's called given information. That's something that kind of works a lot here as after we get done with chapter 2, we get into chapter 4. And actually a little bit of chapter 2 as well. We start to do what are called two-column proofs. And if you've known anybody that's been in geometry before, they're probably going to swear about them, which is fine. But what happens here is that you get one side is what we call a statement and a reason. And you're always going to be given blank, some information. Prove something else. Your given information is how you start something. If you're given something to do, you start to do the problem. So if you're given something as a midpoint, well, what do you know about a midpoint? You cut something in half. So you'll be given specifics to use later. Same idea. You're going to use reasoning. You're given information to come up with the conclusion. You do this when you walk into a room. You do this when you see your friends. You can kind of, you've ever heard of the term read the room? When you walk in and you see your friend, you just kind of think, oh, they're kind of down because something's bothering them. And you're like, you're all right. You know, things like that. You know how you sense things. You look at the problems that we were doing yesterday. You were using the information of Bill and Chuck and his wife Brenda, which means Bill wasn't married to Brenda. You were using those information to reason your way out of the problem. Okay? That's what all this is. One of the things we didn't really define yesterday was this. Pattern. What's a pattern? Something that repeats. Repeat and repeat. We're in a boat. Pete fell out. Who was left? Okay. What about this? Pete and repeat. We're in a boat. Pete fell out. Who was left? Repeat and repeat. We're in a boat. Pete fell out. Who was left?
Repeat.
Pete and repeat. We're in a boat. Pete fell out. Who was left? It takes a minute or two for us to go, wait, oh, that's really stupid. Yeah. Did you have to explain it to her? Did you just have to explain it to her? No, I was just making sure. Yeah, patterns are things that, it's ways, how do I say it? Something with repetitive nature. Do I want to say repetitive nature or measurable repetitive nature? Because if we say measure, well, we'll just say repetitive, and we'll explain the difference here. Now, I know patterns you can do it any different way. If I say yellow, green, yellow, green, yellow, green.
It's yellow.
You're wrong. Yeah. Blue, orange, black. Blue, orange, black, blue. Yeah, so you can still do it with repetitiveness with colors as well. But when we pick out patterns, if I'm looking at numerically, what's happening? Exactly. You're still doing numbers. You're still finding the pattern to it. It's changing consistently by the same amount. Okay? Or the pattern, it doesn't have to change consistency by the same amount. It can be changing by the same values every time. I think I had one like this where it was 1. What's next? 1/5, then 6, and so on. It's not the same numerical times 2 every time, but what you're doing is you're just adding 1 to the denominator. All right? That's still a pattern. It's just not as definable, algebraically, if you will, like that. Now, when we do number patterns like this, it's something you guys will be able to figure out. We're not asking that you guys write the equations of what's called the nth term for these things. We do that in algebra too. You're still looking at patterns. You're still trying to figure out what certain things are. What you guys just did is that you made a prediction. A prediction, I think a prediction is more than an assumption because you're using data to back it up. Okay? It's a data-driven. All right? You're using what you're finding to be within a pattern to come up with the next thing. So when they talk about weather predictions, it's not a weather assumption. When you're looking at meteorology, they look at models, data. They look at what has happened and occurred in the past when these certain things when certain values in the atmosphere have been the same way, when the wind patterns are this way, when the humidity is a certain point. They run what are called mathematical models to come up with prediction. It's data-driven. Did you know that?
Yeah.
There is so much math in meteorology, it's ridiculous. It's a lot of computer-driven math to be able to do all that. So. Yep. So if predictions are data-driven, I don't know, do you want to call them guesses? I mean, their predictions are based, or you would say your prediction is based upon data. Yeah, it's more of something along those lines. Okay. So, all right, well, let's do this then. Let's look at a couple of different patterns and see if you guys could predict the next couple of terms, okay? Come on, ladies. Remember what the ... means?
Yeah.
And so on and so forth, that works. So, ladies, if I'm looking at these first numbers in the sequence, we have 5, 11, 18, 26.
Just going up by 7. Wait, yeah.
What is it? Why? Plus 6, okay. Okay. Which gave you? What's next? All right. What's next?
55. 56.
Okay, good. Nicely done. Nicely done.
78.
All right.
You're wrong.
Let's try another one. Ladies, come on. I see what your first thought of, you're adding, subtracting, adding, subtracting. But when you get into that, is there a consistent add and subtract every time? And that's where you'll start to realize right away that it's not what you would call, do you guys ever heard the difference between what's called an arithmetic and a geometric series? An arithmetic series is something that's adding or subtracting the same amount between each value. So it's constant. You're plus 3, plus 3, plus 3 every time. Geometric means you're multiplying by a common rate every time. Here, you're multiplying every term by -2. So this would be called geometric. Now, the one above that, that 5, 11, 18, 26, it's increasing by 6, 7, 8, 9, 10, and so on. Is that a consistent, you're adding the same thing every time? No. So that would not be arithmetic, even though you are adding between the terms. So that's a whole thing that you guys will go through when you get into Algebra 2, but I thought I would just throw a couple of definitions at your ways. Again, it's not something you need to know, but there are differences between these types of patterns. So each time here, and another thing that whenever you see signs that oscillate between positive and negative, usually that means there's a common multiplier that's either positive or negative. If your first term is negative, your second term is positive, that meant you had to multiply it by a negative. Whereas if it was 3, anyway, oops. So that's how you're changing signs going through. All right, not terrible? All right. Let's see if I can get you a tougher one.
I like
What do you got?
Hey Siri.
Hold on. That was good. That was good. Sorry. Go ahead. That was good. Times 5, times 6, times 7. You were close. Times 8. What do you think the next one would be? And so on and so on. Okay. All right, what about this one? What happens if you have letters?
You subtract it. Like subtract half hours. That's
It's a good idea. See what happens. Well, you just threw her under the bus in that one, right?
Wait, A, B, it's actually close something.
I don't know. See, take a minute, see if you can figure this out.
Okay, I think I'll figure this out. It is one. It's from this one.
What is? What do you got?
Oh, mine is 4.
So it's from J to F is 6, you're saying?
I think it's 4. It's 4 and 5.
So what's your alphabet? A, B, C, D, E, F, J? So I don't think there's 6 apart though. 4. That's what you meant to say. Okay. All right. What about after that? So you're at like. So are we having a hard time with the alphabet here, ladies and gentlemen?
I think it's just right now.
7. Okay.
And then it's 10. So 13.
They're 13 away. Now, let's look at it this way. Is that helping you in? It's possible. I don't know. So, multiply by 2, subtract 1. Okay. So what by your rationale, multiply by 2, subtract 1, multiply by 2, subtract 1. So then you multiply by 2, you get what? 26. Subtract 1, you'd get 25. So what's the 25th letter? Okay. So what you're thinking then is that your educated guess would be 25, yours would be at Y. Now what happens? But what does the ... mean though? There's something else after that. Not that I'm aware of, but I know that there's there's other terms after this. Now, what if I do this? What if I give you a hint to what the next letter is? What is it?
Oh, it's going back to F and then
Nope.
Oh, I know what it's doing. So like it's like going this, then going back. It's like going forward, then going back.
So you think, what's the next letter you think then?
It could be F.
What if I tell you it's not?
So it's not going back to F.
It's not going back to F. It is not.
It's T.
No, it's not A. I know what it is. I see what you're going with. You're trying to do here.
It's our community.
Yes, already said it. Say what? J? Okay.
No, not that. Yeah.
It's F.
Dang, I told you. So then.
You're right. What's next? A. Nope. J.
It'll be A.
It's A.
It'll be A. It's F.
Somebody already said it.
What? J. Oh, I don't get this. Oh. I think we just like something. Oh, that's what y'all.
You're just screaming letters here. You're wrong, but
Am I wrong?
well, those 3 are correct.
Okay, can you just tell us?
What if I told you the next ones were?
Are you spelling a word? It's great
No.
word.
I just ran out of space.
No shit.
When you say J, I thought you had it when you said J. So now, hold up. That was good. Now, now, what's good about doing stuff like that? It makes you guys realize that not always is there some definitive plus or minus numerical value within things. You have to think about the whole scenario here. Okay. You have to think about the whole scenario. Let's see. What's that? You want to know? All right. All right.
They got it. Oh, it's time. It's a clock.
Hold on. All right. What is? Now, what I'm saying, what is the 12th term here? I'm just gonna call this. Which one's gonna be the 12th term?
Like right.
If this repeated itself, what would be the 12th? What would be the 12th one of the sequence?
Yeah, 4, 4.
It would be D, right. And the 12th term has to be D. Now,
Because it's like 4.
because how many terms?
3 times.
Yeah. How many terms are in the sequence? There's 4 of them, which means they repeat every 4th term. So what's 12 divided by 4? Is there any remainder? No. Now what if I say what is the 267th term?
So it's like, you gotta figure out how many times. So, 4 goes into 4.
Okay. All right, so let's divide this out. 4 goes into 26, how many times? 6. How many are left over? 2. 4 goes into 27, how many times? 6. And there are remainder of 3, which means what would your term be? 1, 2, 3. It would be C.
Whoa, that's so true.
When you see stuff like this, it's a very common standardized test question where they give you a pattern that repeats itself X amount after X amount of terms. What you always do is take however many terms there are in that sequence, and if they're asking you for 267th term, divide that by however many numbers are in there, and then your remainder, ladies, both of you, stop. So, when you guys are doing this, your remainder values go 1, 2, 3, no remainder.
Should we write this down?
It's just a little trick. I mean, instead of, thank you guys, instead of sitting there and counting out 267 times, you can actually go through and realize that they're just repetitive upon themselves. Okay? That is a very, very common thing. Okay? Now, the other bit I wanted to do here was, let me that's my wrong sheet. I don't have it. Ladies and gentlemen, is this free for all time? No, it's me answering the question while I pass out a piece of paper. Please keep it down. Now, on this one here, go back. One of the things I want to take a look at is the example here that deals with conjecture. So, on this page, take a look at number 27. I'll get that. Take a look at number 27. Number 27 says, shh, guys. Number 27 says, make a conjecture for this scenario. The sum of 2 odd numbers. Now, make a conjecture means what is the result of the sum of 2 odd numbers. Now, what does sum mean again? Add. All right. Odd numbers. Give me an odd number. 5. Give me another one.
7.
What's 5 plus 7? 12. Okay. Give me another set of odd numbers.
It's basically saying the sum of 2 odd numbers equals 1.
So if I say 3 and 9, what do you get?
Well,
So your conjecture, your educated guess that you come up with via showing some work there, that's what it means by showing your work. What would your conjecture be of the sum? The sum of 2 odd numbers, the sum of 2 odd is even. Yeah. Okay. Sum of any 2 odd numbers is even. That's what you come up with in terms of a conjecture. That's what that means. Okay. Now flip it over. And let's look at 33. 33 says, find one counterexample to show that each conjecture is false. So what we're trying to do is figure out some way to show that this statement is false. What does supplementary mean again? They add up to 180. So what they're saying here is their conjecture is the sum of two angles. If the sum of two angles is supplementary, one of the angles has to be acute. There you go. Your counterexample, a counterexample, we label it as CE for counterexample. The counterexample to that conjecture would be, well, that's false because you could have angles 90 plus 90 to be 180. Now, 90 degrees is what kind of an angle? Right. It's a right angle, which means it's not acute, nor is it obtuse. So that's the idea here. Can you come up with a way to negate that statement? Can you figure out a false part for it? That's what counterexamples mean, right? We just haven't written it like that yet. We've just kind of talked about it. Right? Does that make sense? Let's see, where's the other one here? So, on this sheet, this is out of the textbook. I just figured it was easier to make a quick little copy here. I want you guys to do numbers 6 through 14, 22 and 24, 27 through 30, and then 34 to 36. The first handful are those number patterns. Can you find the next? I think it says one of the next two terms in the sequence. Those numbers in the sequence should be pretty darn simple to figure out. For example, if you look at number 6, it says 5, 10, 20, 40.
Oh, we did that in class.
I know we did. We're paying attention. Okay? So that's the idea as we walk through those. There should be enough room on here to get most of that done. If not, just grab a separate sheet of paper and show some of the work on there. So I didn't want to do too much of it. I thought it would be pretty easy. The only other part that we did not talk about, I'm not worried about the multiply. I didn't want to draw the figures with colors because this was not printed in color. So go from there. Okay? Questions? We got a couple of minutes. Oh, wow. We've used up a lot of minutes. But, oh well. You can probably at least get some of the pattern ones done before you walk out of here. I don't remember my pen went. Okay. I posted that on the calendar also in case you don't write it down. I'll go from there. Tomorrow we will be doing what's called converse, inverse, contrapositive. It's working with what are called conditional statements. A little bit of writing tomorrow, I'm sorry.